All right. So I want it real soft anyway. Okay. So greetings YouTube, beautiful mind here. Here we're going to be, this is going to serve as our lecture for calculus. This is week 6. This is week 6, day 12, section 3.4. In this section, we're going to be exploring finding absolute max and min values, right? So I think before, so again, 3.4 optimization, finding absolute maximum and minimum values. Let me see my time. So some objectives here, we want to see how to find absolute extrema using maximum and minimum principle 1 and find absolute extrema using maximum and minimum principle 2. So I think before we found local or relative max and min or local extrema. So now we're going to explore how to find the extrema over the entire, absolute. So instead of local extrema, absolute extrema for an entire function over the entire domain of a function. Okay, so we have a definition. Let's see. Suppose that f is a function with domain I, then f of c is the absolute min if f of c is less than or equal to all f of x for all x on this interval I. F of c is an absolute max if f of c is greater than or equal to f of x for all x in I, okay? So a continuous function f defined over a closed interval ab must have an absolute maximum value and an absolute min, right? So the main thing here, like, okay, if we're going to be finding the absolute max or min, let's see, hopefully this isn't too loud. Let me turn it down just a little bit. If we're trying to find, I think it is too loud. Let me turn it down some more. Okay. So if we're trying to find the absolute max and min, we're essentially going to do the same thing that we were doing in the previous section, but now we also test our endpoints, A and B, right? So the absolute max or min might occur somewhere in the interval, or it might be the endpoints. Okay. All right. So suppose that f is a continuous function defined over a closed interval AB. To find absolute minimum, max, or min values over the closed interval, first find the derivative, then determine all critical values on the closed interval. That is to find all c on this interval for which f prime is equals 0 or does not exist. Let's turn this down some more. Yeah, that's okay. List the values from step B and the endpoints. So then we have our endpoints and any critical values between A and B. And then evaluate f for each value in C. And then the largest of these is the absolute max. The smallest of these is the absolute min, right? So basically, again, we redo what we did in the previous section, but now we also test the endpoints, and then, whichever has the highest value is the absolute max, whichever has the lowest is the absolute min. Find the absolute max and min values of this function over this closed interval, right? Let me actually create some space for myself. So I'm going to get a copy. Let me get rid of this. And I want from here, basically. Yeah, from there to there. Okay. And I'm going to add a page right there. And I'm going to drop this right there. Okay. We're going to put you here. Let's do view, seamless, view, no, paper, graphic. Oh, okay. All right. So we have this example. Okay, I'm not going to worry about that. So let me get a copy of the original. So we have this f of x. Did it change that? It surely did. We have this f of x equals x cubed minus 3x plus 2, right? So we're asked to find the absolute max and min. So first let's look at the derivative. So then f prime is going to be 3x squared minus 3. That's it, right? So then we need to find out when the derivative is either 0 or undefined. This derivative won't ever be undefined, so we need to find when is it going to be 0. Okay, so if we say 3x squared minus 3 equal to 0, and solve, we add, divide, we get x squared equals what? 1. So then x equals plus or minus 1, right? And notice that plus or minus 1 is in, both of these values are inside this closed interval at the top. Okay. So then now, like, we need to consider, so like if this is the positive x, this isn't going to be drawn to scale, but say here's -1, say here's 1. God bless me. Here's 3/2, and here's -2, all right? So then we want to see, so we have our critical values along with the endpoints. Then we want to plug these into the original, right? So I think yeah, I guess we can do it real quick. It shouldn't be too bad. So -2 to the power of 3 is -8, plus 6 is -2, so that one's 0, all right? Yeah, that's 0. So this y value is 0. When x is -1, this is going to be -1 plus 3 is 2, plus 2 is 4. This one is 4. When x is 1, that's going to be a 1 minus 3 is -2, then 0. So this is 0, and then 3/2. 27 over 8. Let me see. So we get this 27 over 8 minus 9 over 2, 36 over 8 plus 16 over 8. Well, let's see. What's that difference? 3 and 6 is 9, so that's a -9. 7 over 8. So this one is 7 over 8. I'm going to ask Siri really quickly. 3 over 2. Hey Siri, what's 3 over 2 times 3 over 2 times 3 over 2 minus 3 times 3 over 2 plus 2?
3 over 2 times 3 over 2 times 3 over 2 minus 3 times 3 over 2 plus 2 is 0.875.
0.875. Hey Siri, what's 7 divided by 8?
7 divided by 8 is 0.875.
Okay. So then the absolute max, the highest one is the 4, so the absolute max value is going to be 4 when x equals -1, and then the absolute minimum value is going to be, it looks like we have 2, because we didn't get a negative there. It's going to be 0 when x equals -2 and 1. Okay, so these were the results that we got. Okay, style like this. Okay, let's compare that to what's already in the notes and see how do we do. So, with these questions, I don't look at them in advance. I do them on the fly. That's how I feel like it's the most genuine expression. So, sometimes it does get me in trouble. So let's see, how do we do here? View, not single, it's single page. Okay. All right. So f prime, I think we got that. It exists for all real numbers, and it's going to be 0 when x is plus or minus 1. We got those same results. We got those results. So the absolute maximum value of f on this interval is 4, which occurs when x is 1. The absolute min is 0, which occurs when x is 2 and 1. I think we got both of those. Okay. All right, that was fun. Let's try another one. I usually leave these as exercises. If you ever want to work through any of these together, just let me know and we can do it. Okay, I'm going to let that be. Let's look at this. We have a maximum minimum principle 2. Suppose that f is a function such that f prime exists for every x in the interval, and there is exactly one critical value on the interval for where f prime is 0, then f of 0 is the absolute max over the interval if the second derivative is negative, right? So if the second derivative is negative, that means our function is concave down. That means we would have a max value, right? F of c is the absolute min if the second derivative is positive. Okay. Find the absolute min. Okay, so we probably have to use the second derivative. Okay. Let me do the same thing I did in the last one to give myself some space. So I'm going to get a copy of this. I can delete that. What's my time looking like? Okay, I think we're good on time. Probably would be better if I add a page beforehand, but that's okay. Come on. I'm going to drop it right here. Absolutism. Okay. And then let's do view seamless. And I think we're okay for now. Okay. All right. So absolute max and min over this closed interval. So the original, our f of x, we got this 2e to the 3x. Okay, now we want to consider f prime. The derivative of e is itself, and we kind of have to use the chain rule here. So this is going to be 2e to the 3x times the derivative of the exponent, so times 3, which is just going to be 6e to the 3x. Okay, so then we want to find all values of x that make this derivative either 0 or undefined. Let's see. Well, exponential, I don't think the exponential will ever be 0. We didn't move it up or down, so we can't get it to be equal to 0. Let me see. Yeah, because if we set it to 0, it doesn't. We don't. It doesn't. The domain, like the range of e, is above the x-axis. So, will this ever be undefined? Let me see. If we set it to 0, we would get e. Natural log of 0 does not exist, right? So we can't do that. And I don't think this will ever be undefined either. Oh, so I think our first derivative is like our first derivative test is inconclusive. So then we're going to look at the second derivative, right? So we're going to evaluate the second derivative over this interval, and then look at when the second derivative is either. We're going to look at the sign of the second derivative. So let's just look at the second derivative. F double prime of x. So if we take the derivative again, this function, its derivative is going to be itself, which is 6e to the 3x times the exponent, so times 3. So that's going to be 18e to the 3x, okay? Let's see. We kind of got the same thing going on here. Oh, okay. So I think any x that we choose here, like we want to determine the sign. I think it's because it's not changing signs. It should be the same throughout. So like if we just choose an x value and then if it's positive or negative, it should stay positive or negative the entire time. And also if you think of the graph of exponential, it's like it's a curve, right? And I think that curve persists throughout. So it just has the one concavity. For instance, like if I let x be 0, we get positive 18, right? So the second derivative is positive. That means our original graph is going to be concave up. So that means we should have an absolute minimum value. Okay. I feel like we're missing something. We could do the endpoints. I want to say it's monotone increasing. I think the only values that we're getting to test are the endpoints. So, and I think it's just going to be the endpoints. Like if we plug those in, we're not getting anything that's lower or higher than these. Yeah, I think it's just going to be the endpoints. I'm going to kind of let that be for right now. If we plug in the endpoints into the original, we'll get an output, but I think it's just going to be the endpoints. Let's look at the explanation from the text. So we're going to go back to single page. Okay. So now, if we compare to what they did. So f prime is defined for all real numbers. Note that this is positive for all x, right? This is above the x-axis, right? This is positive for all x. So therefore, there are no critical values and absolute extrema must occur at the endpoints, right? I think that's the conclusion that we finally came to. So then once you plug in the endpoints into the original, we'll get this result and this result. So then the first one is our absolute min and the second one is our absolute max. So maybe we didn't even need the second derivative there, but yeah, okay. So again, because we didn't have any critical values, the extrema occurred at the endpoints there. Okay, that was interesting. Find the absolute max and min values of this one. Okay, let's give this one a go. We're gonna do the same thing. Let me give myself some space, but let me add a page first before I do that. So let's get a copy. We don't need this one. This, 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 this. Okay, we're gonna drop it right here. Boom, and expand. Come on. All right. Let's do view. Seamless. Okay. All right. Find the absolute max and min values. Okay. So now this is over the entire domain, right? Before we were given a closed interval where we could test the endpoints. So now we want to find the absolute max and min considering the entire domain. This should be a parabola that opens downward, right? So we should have an absolute max and no min. Okay, let's see. So we have this f of x. We got 4x minus x squared, okay? So let's look at the derivative, f prime. I'm gonna put it in descending power order, but we're gonna get negative 2x plus 4, right? And just for the sake of it, I'm gonna go ahead and look at the second derivative as well. Oh, that tells you a lot right there. Second derivative is negative 2. It looks like the second derivative is always negative, concave down. That means, yeah, that confirms what we were already thinking. Okay, so, so then the critical values are going to occur where the first derivative is either 0 or undefined. This first derivative will never be undefined, but it can be 0. So if we set the first derivative equal to 0 and solve, subtract and divide 2, right? So then our critical value is going to be x equals 2. Then I don't think we have any other endpoints to test. So the only thing to test is that should be our maximum value. Again, we're using the second derivative. Because it's negative, that means the original function is concave down. We only have one critical value when x equals 2. So then that point, so then we should have an absolute maximum value of, when x is 2, 4 times 2 is 8, minus 4 is 4. Absolute maximum value of 4 when x equals 2. Right? And then there's no absolute minimum value. Okay. All right. Let's go like this. Like, I really like this kind of stuff. Like, I know it's a little bit, you know, the presentation is what it is. And I don't get to talk about this often. Like, to look into it, I don't, because I don't teach it all the time. But I enjoy it. Like, it's fun. Um, okay. So let's go view. We want to go to single page. Okay. So we got an absolute maximum value of 4 when x is 2, but no minimum. And again, you know, from college algebra, notice the highest exponent is a 2, so it should be a parabola. The leading coefficient is negative, so the parabola should open downward. And that's, you know, that's what we get off the rip. So then and then we could even use like the vertex formula. X equals negative b over 2a. So negative 4 divided by negative 2 is a positive 2, right? Yeah, so it all kind of checks out. because I mostly find myself teaching college algebra, so it's like we're always, I always want them to see some of this stuff, but you can't talk about this in college algebra like this without terrifying people, even more so than they already are. But you can flow between college, any of the different techniques, and they all back each other, and that's just like that's exciting to me. Anyway, that's neither here nor there. So I think we're done with that one. Find the absolute max and min values when no interval is specified. We consider the entire domain of the function. In this case, the domain is a set of all reals. So we found the first derivative, and then x equals 2. Since there is only one critical value, we can apply the principal 2 using the second derivative. The second derivative is always negative. That means the original should be concave down, right? So then since the second derivative is negative, and when x is 2, y is 4, f of x has an absolute max value of 4 when x is 2. F has no absolute minimum value, because if we have a parabola open and downward, it goes down forever, so there is no absolute min. All right? Okay. I think we might. No, we got a little bit more to go. We're actually getting through this rather quickly, much faster than I anticipated. I usually leave these as exercise for you. I would definitely give these a go. You want to make sure that you're getting these concepts. Yeah. Okay, let's look at this strategy for finding absolute max and min values. To find the absolute maximum and minimum values of a continuous function over an interval, find the derivative, find the critical values. If the interval is closed and there is more than one critical value, use the maximum minimum principle 1. Principle 1. If the interval is closed and there's exactly one critical value, use either the max min principle 1 or max min principle 2. If it's easy to find the second derivative, use max min principle 2. Okay. If there's an interval that is not closed, such as all reals or open interval, or something of this function of a function that only has one critical value, use max min principle 2. In such a case, if the function has a maximum, it will have no minimum. If it has a minimum, it will have no max. Okay. Find the absolute max and min values of this function over 0 to infinity. Okay. So let me add a page. Give myself some space. Add a page. Let me get a copy of this. Let's get rid of that. Yeah, I have to check on her. Okay. We're gonna drop it right here. Expand. All right. And then let's do view seamless. Okay. So let's give this a go. So let's see. First, let's get a copy of the original. We got 5x plus 35 over x. Okay. I'm going to rewrite this. Let me see. I think I'm okay. Let's look at the first derivative. That's going to be 5. Let's see, the bottom times the derivative of the top minus the top times the derivative of the bottom over the bottom squared. All right. There are a couple of ways you could do that second part. Eventually, you'll get to this conclusion. So I'll let you kind of work that out. And let me do this. Get rid of this and move that to here. Okay, and let's go ahead and do the second derivative. I think we can do it. I don't know why I'm writing like that. Okay, the second derivative, bottom times the derivative of the top. Let's see, that's a 0. Bottom times the derivative of the top minus the top times the derivative of the bottom over the bottom squared. Okay, so then this becomes 70 over x to the power 3. Okay. All right. So we can't use the endpoints here, right? So I think we do have to use the second derivative test. Let's see let's find any critical values first. We want to find out when the first derivative is either 0 or undefined. Let's see, can this ever be 0? If we set it to 0, what happens? Can that be 0? Can that be 5? I think we might be able to. I think we can find when it to be 0. It can be. It's going to be undefined when x is 0, right? Let's set it to 0 and solve. We got this 35 over x squared equals 0. So this should be the same. Let me see. 5 35 over x squared. So then x squared should equal what? 7. I'm going to continue over here. Or actually, that's fine for now. So then x would be plus or minus the square root of 7. Okay. And then it's going to be undefined when x is equal to 0, right? So we at least got 3 critical values, but then we only want to consider the ones on the interval from 0 to infinity. So we don't include 0. The only thing that falls in that range is the positive root 7. Okay. So if I add a page, we're not going to test the endpoints here. So here's positive x. Here's the square root of 7. If we plug root 7 into the second derivative, it should be positive, right? The cube root of a positive is still positive. A positive divided by positive is positive. So the second derivative is positive. That means the original function should be concave up, which means this would be our absolute minimum value. Yeah. Yeah. With the open endpoints like that, you can't test the endpoints. So then you have to use the chair. Did something funny. Let me see if I can get this thing back. No. Here it is. There we go. Yeah. Let's see. Yeah, we can't test the endpoints because it's open intervals. So that's why we use the max-min principle 2, where we look at the second derivative. The second derivative here is always positive, which means the original function should be concave up, which means we would have an absolute min and no max, right? So we should have an absolute, I can't write today, absolute minimum value of, we need to plug root 7 into the original. Okay, let's do that. So if we have f of root 7, that's going to be 5 times root 7 plus 35 divided by root 7 plus 35 divided by root 7. This is going to be the same as 5 root 7. 35 divided by 7 is 5. It's 10 root 7. Okay. So it has an absolute minimum value of 10 root 7 when x equals, or at an x value of, nope, when x equals root 7. And then there was no absolute max. Okay. All right, let's give that a go. Let's see what happens there. Okay. View, single, okay. Let's try that. So, the first derivative, since f prime exists for all values, the only critical value for those where f prime. Oh, yeah. We ended up, we knew that 0 worked, but again, that's not in our interval that we were considering. So remember, that's why we didn't, so we got the same thing. That's why we didn't use the 0. If we set it equal to 0 and solve, I think it got the same result that we did. So it should be plus or minus, but on the interval from 0 to infinity is only the positive root 7. This interval is not closed, and the only critical value is this. Therefore, we have to use principle 2 using the second derivative. So I think we got the 70 over x cubed, which is always positive, or when you plug in root 7, it's positive. Has an absolute minimum, 10 root 7. Man, it's like magic. All right. All right. Let's go on to the next one. I think we might have one more. So the absolute minimum value of this, there's an absolute minimum value of 10 root 7, which occurs when x is equal to root 7. And it has no absolute max. Okay. Then we got a quick check, and that might be it. Let me see. Yeah, that was it. So we got finished a little bit early. It only took us like 30 minutes to get through that. We don't have to use the full hour and 15 minutes, but we do have it. I don't want to keep you beyond the hour and 15 minutes for these concepts. Okay, so that was the last one. I know the last one we got a little bit dicey, but with practice and like I felt like these examples weren't as bad as the other ones. Some of the examples do get a little bit like, it gets bad. Like it can get bad fast, but the ideas are not that bad. It's just the application sometimes could be a little bit detailed. Okay, but this one wasn't bad. It was fine. Okay, so we looked at an absolute minimum. Here, let's go here. An absolute minimum of a function is where that f of c is less than or equal to f of x for all x in the domain. Absolute max is where f of c is larger than all f of x for all x in the domain. If the domain is on a closed interval and is continuous over the domain, then the extreme variant theorem guarantees the existence of both an absolute min and an absolute max. Endpoints of closed intervals may be absolute extrema, but not relative extrema. Right? If there's exactly one critical value where f prime is 0 in the domain, then the max print may be principle 2 may be used. Otherwise, principle 1 has to be used. And I think that was it. Okay. So yeah. And on that note, we're going to end the session here. And from one beautiful mind to another, enjoy the rest of your day. Peace.